Greetings, Louis. Yeah, I'll probably start in about like another 30 seconds or so. Can everyone type or are there any issues with that? Hey Ellie, how you doing? Okay, so I'm guessing you guys are on here because A, you are not ready for the physics exam, or B, you just want an extra practice. So what I'll do is I won't make this an hour because it's way too long for you guys. I'll try to make this maybe like 20, 30 minutes or so, but I'll give you everything you need for the exam. So first things first, do you guys all have paper and pen and the calculator? Because that will probably help. Otherwise, yes, Joshua. Okay, so let's start off with energy first, because I'm pretty sure they'll throw in a question to do with that. So, first things first. What we need to know is the very first equation. Do you guys all have this equation memorized? So energy is power times time. Because this thing is probably the most common formula they give you in the exam. It's for both energy and electricity as well. And yeah, they give you quite a lot of marks for it. So you have to memorize this, by the way. They do not give you this. I had a sneak peek at the exam, and there's no formula sheet that I can recall. So everything they're going to give you is memorization questions. Okay, so first question, if I told you the energy was 30 kilojoules, and if I maybe give you the time as 2 minutes, they might ask you what's the power. So, and it might be like a 4 marker. So try solving this. I'll solve this at the same time as well. The key things in year 10, year 11 is they always give you weird like units. We know that with time, we always want the time in seconds and not minutes, and you want your energy in joules and not kilojoules. So we have to convert both this and this to their respective units. So to go from kilo to the standard units, if you think about a kilogram is 1,000 grams. So you multiply by 1,000. So you guys, I believe, end up with 30,000 joules there. And to convert from minutes to seconds, you just times by 60. Yeah, because there's 60 minutes. So sorry, 60 seconds in a minute. So now that you have your normal units, you just put them in the triangle. If we're trying to look for power, it will just basically be what? Energy divided by time. So your energy is 30,000 divided by 120, and you get an answer which I cannot recall. I believe it's maybe this. Just guessing, not sure. 250 or 25, and you end up with watts. You guys have the calculators anyway. So yeah, that's that. Okay. So is everyone okay with this kind of question if it shows up in the exam? Just make sure that you double check your units. But apart from that, they can't really throw anything else. All right, you guys are a bit too smart then. Yeah, 11's find this hard. Okay. Next thing is when we have to deal with efficiency. So when we talk about efficiency, I'll give you guys an example. Say you have a kettle, right? And with this kettle, actually, you know what? I might as well just show you guys in my kitchen one sec. You'll get an super sneak peek. Never seen before. Okay, wait, let me just turn this on. All right, if you guys look here quickly, right? So every single microwave, I believe, has like a rate in there. So my one says 800. The other one might probably be a bit more because I'm broke as hell, but there you go, 800. If I give you guys this kettle, oh god, never mind, it has water. Someone set me up, never mind. But I believe this one says, why is it, just wait, yeah, it says about 2,500 to 3,000 watts. Why is this not, sorry guys, I think the flash is making it impossible to see. There you go, 2,500 to 3,000 watts. So basically the kettle has about, I think, 4 or 5 times as much power as the microwave. All that basically means is if you guys have double the power, you basically heat up stuff twice as fast. That's all you need to know. Now with efficiency, if you think about it, say that like, so from the power socket here, say that this is given, for example, 800 watts, right? So 800 watts of power is delivered here, but do you guys reckon all 800 watts will be used to heat the food inside there or not? Or do you reckon some will be wasted? That's the question. What do you guys think? Is it possible to get 100% useful energy transfer? So all this 800 watts of power, yeah, some will be wasted, yeah. So they might ask you in the exam, what is it wasted as? So obviously in a microwave, you use it to heat food, right? But what you can say is some of it will be wasted because the microwave itself will heat the surroundings, which obviously you don't want to heat this area, you only want to heat the microwave itself, yeah? So I hope that makes sense because they always ask in the exam. Okay, so back to here. So if you just look here, so once again, what we mentioned was efficiency is basically, you need to write this formula down. So it's useful power or energy, doesn't really matter which one, over the total power times 100. So just like I showed you guys in the kitchen, let's say the total power input to the microwave is 800 watts, which is said on the box. But we know that in reality, let's say for instance, maybe because my one's trash, it might only give 400, which is useful. So the efficiency would be 50. Yeah. So that's how it kind of works. Yeah. So based on that, as long as they give you this and this, you can always work out the efficiency of anything in the world. Like all you have to know is that there's nothing in the world that has 100% efficiency. So nothing. Sorry about my handwriting, it's not that good. Nothing has 100% efficiency because energy is always dissipated. Dissipated just means given off. Dissipated to... let's just say the kitchen is not in Loughton. Alright, so we basically have this. Now, let me give you guys another. So this is the second thing to memorize. And then that was the first one again. So moving on to electricity now. If I just give you these circuit symbols, try to label them. So, because they'll probably give you one of these in the exam to label. So you have got this. All right, so let's start off with this. You guys can just comment. If we start off with the first one, what would this be? Yeah, that's a bulb right there. And the next one, this is probably the easiest one there. I think you guys are lagging probably. But let me just put the numbers so you can just keep commenting for each one, like in chronological order. So if I give you these, this one is a, resistor, right? That's a bulb resistor. What would the third one be? Oh, I'll wait for a bit. I think because you guys obviously started the live stream late, so you're kind of lagging behind. I think if you refresh the page, then you probably should be in real time. Yeah, so this is a thermistor. This is a light. Yeah, LDR, light dependent resistor. And then this is... That's a diode. Next one is a... Yeah, and all one's a battery. All right, so these are the stuff you kind of have to know for the exam. There are a few extra ones, like for example, you need to also know a cell. But more importantly, these are the ones that they might ask you the function for. So this, and this. You just need to know what these do in a circuit. And for GCSE, especially if you're going to get if you're doing a higher paper, you need to know quite a bit about these. Okay, so let me just show you what thermistor does quickly. So for a thermistor, I don't know who your teacher is for physics, but they probably did explain this before. but I'm just going to do in depth again. So thermistor. Oh, so the thing is, no, a thermistor, good, very good. But the thing is, the thermistor doesn't control the heat. Like most students, I think they get told that it does control the heat. Where I'll kind of just go over it again, don't worry. So with the thermistor, it's a resistor, and the thing is, its resistance will keep changing depending on the heat. So the heat is the one dictating what happens. So resistance changes according to temperature. Yeah, so that's the official definition according to. Yeah, Mr. Beddy and Mr. O. Yeah, they're good teachers. So resistance changes according to temperature. Let me show you how. So what you need to know is when the temperature, I'll just write hot there. There's no specific number, just when it's getting hotter, your resistance does the opposite. So the resistance of the thermistor will go down. And then scenario 2 is when the temperature is colder, getting colder, your resistance goes up. These are the things that you definitely have to know, especially if it's in a higher paper. Yeah, so you don't need to know the logic behind it. Oh, that's like university level work. But what you need to know is that if it's very warm, then your resistance of this specific device will go down. Yeah, and the graph for this, because even if it doesn't come up in the exam, it's still going to be useful for your GCSEs regardless, so it's worth learning. So the way it works, you get a curve like this. They don't really care how you draw the curve as long as it's just in this shape. Yeah, obviously you can't make it completely accurate. So you have resistance here, and as we said, resistance keeps going down as your temperature keeps going higher. So yeah, so as you're increasing your temperature, your resistance is falling down, as we said there, and vice versa. If your temperature is getting colder this way, then your resistance is getting higher. Okay, now calculation questions. Okay, so are you guys okay with this, or do you need more time to copy this? This is like anywhere from like grade 7 onwards, to be fair. These are quite hard concepts. Okay, that's good. You see Ohm's law. This is this is like the main part of electricity here. V equals IR is a simple formula, but this pretty much comes up every single year in every single official exam. So so V stands for voltage. Does anyone know another name for voltage that they might use in the exam? Because they don't always use the word voltage. Anyone? No? Alright, so density will not come up in the exam, mommy. So you're lucky. It'll just be energy and electricity. So you see but I can still go over another time. So instead of voltage, they might use this word. Very important, because if you see this in the exam, you're probably thinking, what the hell? But it's the same thing as voltage. Yeah, so potential difference is another word for voltage. Did your teachers explain exactly what this concept means? As in, like, not just tell you that it's the same, but did they explain what potential difference is in real life, or? Okay. Because I think Ohm's law was the first thing you learn electricity in year 9. So I don't know, you guys probably started electricity mid-year 9, I'm guessing. Okay, that's good. I'll just go through it quickly. Now you see in a battery, because once you get circuit fundamentals, then everything else is easy. In a battery, when you buy it from a shop, if it says 6 volts, that means one of the ends of the battery is obviously positive, one is negative. One of them will read 6 volts, the other one will read 0. So the difference between both ends of the battery is 6, right? So potential difference just means the difference in voltage between two areas. So if I draw a circuit for a battery, let's just say, and there's a light bulb there, this battery is just that in a different form. So let's say this is your negative side, your positive side. If this is like 6 volts there, and this is 0, the difference between them is 6, right? So electricity always works, or current always flows in something when there's a difference in voltage. Yeah, so because there's a difference between there and there, electrons will flow across the battery. But the thing is, if I gave you this scenario, guys, 6 volts and 6 volts on both ends of the battery, would any electricity flow in this circuit, do you reckon? If both ends of the battery are 6 volts. Anyone? Would the electricity flow through here if, unless you guys are like ages behind somehow? Hey, Bobby. Oh, but you see, okay, so Louisa, you said yeah. Okay, you guys are saying yeah. But okay, so you see potential difference. Let me take one step back quickly. Because I know I have a feeling that this was not explained in year 9, so it's worth doing this properly. Okay, so this is a road, or this is circuit. Let me give you an analogy. So this is your circuit here. Oh, I'll start from the basics, don't worry. I have a feeling your teachers probably just went through what the textbook says rather than like in depth. So this is just a normal circuit. I'll go through everything so that you guys will understand it. And then let's imagine that this is a resistor. And then here's like another resistor. So there's two resistors. Nah, I don't think he's a bad teacher. So this drawing just looks like this basically. So yeah, so this circuit is the same as that. I just made this into like a road. It's a 3D model. What, Bobby? No. So basically, battery, and then you have resistor. Then now let me like link this to real life. So in real life, when you guys were kids, I mean you're still kids, but I don't know if you guys had this, but I'm a bit old school. So you say you have like a toy kit, and you have basically a miniature road, right? So you have a miniature road there, and you have like cars. I'm pretty sure you guys had this when you're like a lot younger, and you just basically move the cars across the tracks here, right? Now, I'm gonna link this to like electricity. So the way this works is, let's imagine that you have like a big coil of spring here. Yeah, so you got a massive spring. Let me ask you a very simple question. If you kind of compress the spring and release it, what will happen to the cars? So say you make the spring very compact, so you apply force and then you release the spring. What do you guys reckon will happen to all the cars here? Yeah. So as Bobby said, all the cars will start to move, right? So the cars will get a lot of force. All the cars will start to move around the circuit or around the track. Okay, that's good. This spring, I want you guys to look at the analogy. So the force from the spring is the same as voltage in electricity. So what the voltage does in electricity is the same as what the spring does to these cars here. And each car in electricity represents the electrons. Yeah, so what I want you guys to understand once again is voltage is the force that pushes electrons around the circuit. Does that kind of make sense? So instead of the spring is just a battery, the battery you can imagine is like a spring. It literally pushes electrons, which are stationary, obviously, in the beginning. They're not moving. So the battery literally gives them a good kick and moves them across the circuit. Okay, so now I want you guys to think, if there's more voltage, if your voltage or if your spring is stronger or if your battery is stronger, what will happen to the speed of these cars or electrons in the circuit? What happens to the speed? Yeah, so they go faster. That's good. Okay, so the first thing we already said was that voltage is the push. Now current, because they all just weird words, right? Current is basically the speed of the electrons. Yeah. So all I've done was just use cars as an analogy for electrons. So obviously, the greater the voltage in the battery, then obviously the faster the cars move, aka the faster the electrons move. So what we can decipher from here is if your voltage goes up, then your current also goes up. Does this like make sense now? As in how I kind of linked the battery to the spring, and the battery really just only applies a force moving electrons around the circuit. Yeah, and the greater the force or the greater the voltage, then the faster they move. Okay, that's good. Now on a road, let's look at the third thing called resistance. Resistance on a road would be what? The same as speed bumps, right? So if you have speed bumps in a road, like next to school areas, we know that cars are going to be forced to slow down, otherwise they'll get damaged. So resistance can be represented by speed bumps. And the way it works is we just say resistance is obstacles on road, right, which slow down the cars, or in the real case, the electrons they get slowed down. Yeah. So these are the three main things in electricity. If you get this, other things will start to make a lot more sense. Yeah. So what we need to know is now if your resistance increases, so if there's more speed bumps, what do you guys reckon happens to your current, aka the speed of stuff? What do you reckon happens? So if I increase my resistance, aka more speed bumps, what would happen to the current? Yeah, so it'll go slower, so your current goes down. Yeah, so your current decreases because there are more obstacles now. Okay, so that's good that you guys get this. Now I want to link resistance and voltage. This is the one that, unless you use this analogy, it wouldn't make sense. Let's say that in scenario A, I have a massive speed bump, and scenario B, I have a tiny speed bump. Remember, voltage is the force to push things across something, right? So let's imagine you have your car, your electron, trying to get over this. In which of these two scenarios will I have to apply more voltage, do you reckon, or more push to get it over it? Where resistance is more, resistance is less. Where do you need more push or more voltage? Yeah, all right, you guys are legends, yeah. So basically here, as if there's a greater obstacle, you also need more voltage. Because I think this is the thing that everyone or even up to year 12 don't really get. So what you need to understand is, if there's a greater obstacle, you need more push, aka voltage, to get stuff across. Okay, you guys are getting this pretty quickly. Yeah, so rather than memorizing this just for the sake of it now, hopefully you guys should actually understand the logic behind this. So in the exam, no matter what circuit you get, you can just sketch this next to it. Just remember that, once again, your battery provides a force, aka a kick or something, moving these electrons around the circuit. These resistors will slow down the electrons. And if there's more resistors, the current gets less. Simple as that. Okay, that's the hard bit. The easy bit is now just the formula. So V equals I times R. All they do is give you numbers. So if they maybe say the current is 2 amps and your voltage is 100 volts, what would the resistance be? Let's see if we can find this first. It might be like 2 marks or something. Yeah, it'll be 50, yeah. Yeah, so easy. You guys just done 100 over 2, which gave you 50. And the units for resistance is speed bump, aka ohms. Yeah, it's kind of weird how the units for it represents a speed bump. So to make the triangle for anything in maths or physics or anything in science, the thing by itself always goes on the top, and then everything else goes on the bottom no matter what. Yeah, so that's the triangle for anyone who may not like rearranging. Yeah, so it's 50 ohms. Okay, let me give you a hard one. Let's say you got V is 3 kilovolts. I have an Armani pen, but I have a ghetto kitchen. I have no idea how that works. I'm investing all my money in the wrong things. So let's say, how am I rich? My kitchen is like the size of a bathroom. All right, so R is equal to, let's say, 100 ohms. What would current be in this case? Don't fall for make sure you convert the kilo into just normal stuff. Okay, so, oh, so but if you guys look at the triangle, right? I suggest you guys just make the triangle all the time. If you look at the triangle, if we're trying to look for I is basically what? What's on the top? V is on the top over R, basically. So if you cover it like that, 0.03. Okay, you guys are almost there. You might get half the marks. Remember what we said, we do not, in electricity is very important. You guys might want to write this. So in electricity, we do not use kilo anything. Yeah, Louis got it correct, yeah. You guys done the correct method, but you just forgot to change kilovolts to just volts because, once again, I said 3 kilovolts. We can only want normal volts. So to go from kilovolts to volts, we times by what, 1,000? Remember? So if you see kilo anything, always times it by 1,000 when we deal with electricity when we deal with electricity. So we get 3,000 volts And then R is just R, which is 100. So you guys have to do 3,000 over 100, which gives you 3. Hold up, it doesn't give you 3, it gives you 30. Aha. Josh was correct, yeah. So you get 30, yeah. Are you sure it's 3? Because it's 30,000, right? You're timesing it by 1,000. Yeah, nice one, Louisa. Yeah, so 30. Okay, let me give you another one. It's just good practice because in physics, the way they distinguish between grade 7 and grade 9 students is like by people who can like I guess convert these stuff. So with electricity, no matter what they give you, now let me give you a different. Let's say they gave you 2 kilo ohms. 2 kilo ohms would be how many ohms? Let's see who can do this first. So remember, kilo just times by yeah, perfect. Louisa's right. 2,000. Yeah, that's good. If someone gave you 2.5 kilovolts, how many volts would that be? You guys are lagging behind big time. Yeah, Ellie's connection is the best. Yeah. So we get this much. Wait, what? I wrote volts and then ohms there. Yeah, it's volts. Sorry. So 2,500. Okay, yeah. So just make sure in the exam you always double check your units. Yeah. Another thing is you guys have to memorize this as well. That's the bad news, right? But it's not that hard. V equals IR, so that's decent. Okay. What I'll do is let me go through the last thing now. I don't know how much you guys remember of this from year 9, but I believe it was in the very beginning. Are you guys okay with 6 markers to do this topic? Gravitational. Yeah. So I mean, I'll show you the worst case scenario and just end it. So kinetic energy is what, half mv squared. Pretty sure you guys know this. And GPE is mgh. If you guys didn't memorize this yet, you might as well just memorize it. So there are easier ways to kind of get this. M is just mass. That's probably the easiest thing in physics, just how heavy something is. V is your speed or velocity. But to be fair, some teachers say velocity, but it's actually speed. I'll tell you guys probably another time, but it's definitely not speed, not velocity. Oh yeah, you guys were meant to learn this probably in the beginning of year 9. Don't know who you had back then, but yeah. G is gravity, and then H is height. Yeah, so make sure you guys write this down because these are like really important formulae. Oh, you had Miss Patel in year 9. Oh, okay. So half mv squared and then mgh. There's tips for you guys to remember this. Like the word kinetic in physics is to do with movement. Yeah, so because at university I dealt with like kinetic theory and stuff. Because when I done engineering and like, at uni, so you deal with a lot of like movement of like bridges and different things. So kinetic is just to do with movement, and then GPE is to do with gravitational. So there are like for example, you'll never put this accidentally within that formula because kinetic is only to do with speed and movement. So you kind of remember that there is at least speed and obviously mass because the energy depends on how heavy something is. Yeah, almost all energies. So we have these. The half is there just for the sake of it. I won't show you the proof because that's like third year university stuff. Um, G is gravity. They do give you this in the exam. They give you the value for this in the exam. So they give you value. You're not meant to memorize it. But on Earth is about 9.81. Yeah. So let me give you a basic question. They might say, Mr. Hammond he wears glasses, right? So he's running away from something, and this is his speed. What's his kinetic energy? So it's quite simple, but if you guys calculate it, what should KE give you? So the formula is there. Could be from a dino, if they're still alive. So let's see if you can get this first. Straightforward question, to be fair. You're just putting the numbers in. 200. Yeah, so we do half times, and then your mass is 100, and then you multiply it by your speed, but don't forget to square your speed. So your speed has to be always squared, yeah. So that gives you 0.5 times 100 times 4, which is 200, yeah. And the units for any kind of energy is joules, so J. Yeah, so that's your units for, regardless whether it's this energy, that energy, elastic energy. Okay, now let me give you a harder ones. I have to turn the page, so I hope you guys written this down. Just bear with me 5 more minutes, guys, and I'll be done. So half, let me just write it again. Okay, so the hardest question they can give you is the usual when the guy falls off somewhere. So say you got a man or a woman, doesn't really matter, on a building, and the height is 200 meters above the ground. The person's mass is 50 kg, and they tell you gravity is assumed as 10. So what I'll ask you guys first is find the GPE. So what's the GPE equal? So while you guys are calculating it, let me just explain what GPE is. So it's the amount of energy you store relative to the ground level. So the higher up you are relative to the ground, the more GPE you store, the more gravitational potential energy you store. So it's just mgh, so mass times gravity times height. So you're just going to do 50, which is your mass, gravity, which is 10, and then your height is 200, and then you end up with 100,000. I'll trust you guys on that. Okay, that's good. Yeah, so everyone understands that at this height you have that much energy. Next thing is, let's assume now the guy falls down, right? So when the person starts to fall down, hey Ella, so you see when the person falls down, what's going to happen to the amount of gravitational potential energy as their height decreases? What will happen to this number? Anyone? So as the person falls and the height gets less and less and less towards zero, what should happen to this number there? Yeah, so the number would decrease. Very good observation, Louis. Greetings, Ella. Hope all is well. So it'll decrease. Now the thing is, as it goes down and down, remember this is another thing you guys need to know. Energy cannot be created or destroyed, right? So obviously we can't just say that this energy disappears. It is getting less, but it has to go to somewhere else. Yeah, it's kind of like two bank accounts. So if you have bank account 1 and 2, say they're your own bank accounts, and then say one of them is £0 because you're broke, and then the other one is 100. What's happening is basically if you take 50 from this account and then you bring it to that account, they both have 50 now, which is still equal to 100. So the total money in both accounts will always be the same, regardless of how you swap them around. Yeah, same thing here. As you fall, what happens to your speed? Obviously, you guys probably don't have experience with this because you never jumped off anywhere. But if you were to jump, trust me, the more further down you go, the faster you get. Yeah. So what we need to understand is your gravitational potential energy is getting converted to what kind of energy? What energy is to do with movement and like speed? So yeah, kinetic, perfect, Ellie. Yeah, so they make this quite easy in GCSE. All they say is your maximum GPE at the top, which is that much, will be the same as your kinetic at the bottom. So we can do a cheat code here. All we can say is, yep, Kingsley. So it's kinetic, perfect. So all we say is your kinetic energy at the bottom, right before the person hits the floor, would be the same at the top. So it'll be 100,000. Yeah, that's all we're saying. So all of this got converted to this at the very bottom. Yeah, so that's all we said. So GPE is the same as kinetic. So yeah, is everyone okay till this bit here, or are there some things that you probably don't get? The only reason why your GPE all got converted to this is because as you fall down to the bottom, your height becomes 0, and this becomes 0. Okay, that's good. So now they might ask you for the maximum speed. This might be like a 4 or 5 mark because it's the hardest thing you can get. Maximum speed at the bottom. They won't even say at the bottom. We just now know that the maximum speed will always be at the bottom. So what we can do is we take this equation. Let me make a triangle for this, yeah? So I'm making a triangle for kinetic energy. The thing by itself is always going to be the thing at the top. So kinetic energy is at the top, everything else is at the bottom. So you got half, I'll just write it as a decimal just to make it easier, times what, m times v squared. Yeah, so I've made the triangle a bit slanted, whatever. Yeah, yeah, mommy. On Earth is always 10, but I mean, in questions they might round it to 9.81. They might do whatever they want. So just they'll give it to you. So don't worry about memorizing the number. Okay, so we have this triangle. We know what our kinetic energy is. We'll put a tick there. We know that half is a half duh. And then we know the mass previously is 50. The mass isn't going to change. So we're trying to look for what? Your speed, right? Okay, so if I cover my pen on speed squared, my speed squared, what will it equal to? So if we rearrange this, what should be on top of the fraction that I'm going to now write out there? So on top of the fraction, what do we have? Kinetic energy, right? At the very top. So I'm just going to rewrite it. Basically, you rewrite the triangle without the thing you're looking for, if that makes sense. So I'm going to write the whole thing just without v squared. So it'll be 0.5 times m. Is everyone good till this step here? Same triangle as that. I just took the v squared out because we're looking for it. Yep, Adam, yeah, there's no density or anything like that. So this is what we have. Okay, now let's just plug the numbers in. So our kinetic energy was the same as GPE, so it's 100,000. And then you divide it by half, because there's always a half there. And you times it by m. The mass of the person is 50. By the way, guys, in a calculator, try not to use the normal division sign. You always have to use this one, otherwise you're going to make a lot of like errors in the exam. Just use the fraction sign. Yeah, so make sure you use this fraction sign there. So once you put this in the calculator, what do you guys get? 0.5 times 50 is 25. I think you get 4,000, if I'm not mistaken. Yeah. So you get 4,000, right? Okay, that's not the last step though, because if you guys look at this, there's a squared there. They didn't ask us for maximum speed squared. All they asked us was for the maximum speed. So in maths, how do you get rid of the squared? What's the opposite of squared in maths? So you guys, I'm hoping they taught you. Yeah, so square root. So the opposite of this is a button that looks like this in the calculator. So all you do is when you get this answer, you just say square root answer. And when you square root the 4,000, I believe you get... Now, who am I kidding? I don't know. What's the answer for it? Yeah, 63.25 roughly, yeah. So that's quite fast to be fair. Yeah, so that's the maximum speed of the person at the bottom. All this, believe it or not, guys, will be like a 6 marker. I mean, like, if it's the kind of thing where if you don't really get it, you'll get 0 marks in it. If you get it, it's the easiest 6 marks of your life. All you need to understand is, at the very top, you have GPE. At the very bottom, all of that gets converted to kinetic energy. Yeah, so a lot of people forget that this will equal to kinetic at the very bottom. And then you can find your speed by just using the triangle. You guys are all okay with this if it was to show up in the exam, or? Yeah, it's in class. Yeah, I believe it's on Wednesday, but don't quote me on that. I'm pretty sure it's Wednesday. Yeah, okay, that's fine. All right, guys. So yeah, I mean, these are like the main things for the exam, to be fair. So yeah, I'll be doing, I think, revision on like Monday and Tuesday at lunch if you guys want. If you want to go get food and then come to S1, I'm doing revision like a few year 10, so feel free to join in if you want. But yeah, I think you guys should do well. Good luck with like the biology and chemistry bits. All right, so I'll end it here. Catch you guys on the week. Bye.